Our world is just full of these incredibly complex puzzles, right? Think about financial markets or even our own biology. Everything seems connected to everything else. So, how do you even start to model something like that? How do you figure out how one piece affects another? Well, that's exactly what we're going to dive into today. So, really, the big question is this: how can a machine learn to think in shades of gray instead of just seeing things in black and white? The real world isn't about ones and zeros. It's about maybes and probablys. And it turns out there's this really powerful tool called a Bayesian network that's designed to do exactly that, to reason with uncertainty.
Let's be real, right? The world is messy. It's not some clean spreadsheet where everything is in its own little box. Everything's interconnected, tangled up. Certainty, that's pretty rare. If you tried to build a model that tracked every single possible interaction, it would just become this massive, unmanageable beast. So yeah, we need a smarter way to do this. All right, so to really get how this works, we're not going to start with something huge like the global economy. Nope, we're going to start super simple, right in our own backyard and build a model from scratch. So let's imagine a really simple scenario. We've got just 3 things to think about. Is it raining? Is the sprinkler on? And is the grass wet? Obviously these things are all connected, but the real question is, how do we actually map out those connections in a way a computer can understand? Okay, so this is the key part. We have to figure out what causes what. So, step 1, we start with rain. In our little world here, nothing causes the rain, it just happens. So it's a root cause. Step 2, then we've got the sprinkler. Well, whether you turn the sprinkler on probably depends on if it's raining, right? So we draw a little arrow from rain to sprinkler. And finally, step 3, the wet grass. What makes the grass wet? Well, either the rain or the sprinkler, or both. So we draw arrows from both rain and sprinkler to wet grass. Simple as that. And there you have it. What we've just done is create a map of dependencies. These arrows, programmers call them causal edges, they show us who influences whom. Now notice, this map doesn't tell us how much the rain affects the sprinkler, just that it does. It's like we've built the skeleton of our model. We've got the basic structure of our knowledge down. So believe it or not, that simple little diagram we just drew, that's a Bayesian network. And what's so powerful about it, and this is the key takeaway, is that it separates the knowledge from the reasoning. Think about it, the graph, the structure we just made, that's the knowledge. The math and the calculations we're about to do, that's the reasoning. And keeping those 2 things separate, man, that's what makes this whole thing so incredibly powerful and flexible. Okay, so we've got the skeleton in place. Now it's time to add the muscle. We need to put some numbers on these relationships to quantify just how strong they are. And the way we do this is with something called a conditional probability table, or a CPT for short. Basically, every single item, every node in our network gets its own little table, and all that table does is answer a simple question. What's the probability of me happening given what my parents are doing? And by parents, I just mean the nodes with arrows pointing to me. Okay, let's look at a real example. This is the CPT for our sprinkler. It's actually super simple to read. Look, if is it raining is true, what's the chance the sprinkler's on? Well, pretty low, right? Just 1%. That totally makes sense. But if it's not raining, the chance the sprinkler is on jumps way up to 40%. See? This little table perfectly captures our common sense logic using just a few numbers. It's really elegant. And this right here is exactly why this whole approach is so incredibly efficient. This quote really nails it. Instead of making one gigantic table with every single possible combination of rain, sprinkler, and wet grass, which would get huge fast, we only have to store these little local probabilities. The graph, or skeleton, gives us the recipe for how to combine them whenever we need to. It's so much smarter. Okay, this is where the magic happens. We've built the structure, we've added the probabilities. Now we get to ask it questions. We can finally put our model to work. And this whole process, this is called inference. So what if we want to know the odds of a very specific thing happening? Like, what's the probability that the grass is wet, the sprinkler's on, and it's raining all at the same time? You might think that's a complex calculation, but because of the way we've structured our network, it's actually beautifully simple. We literally just multiply the right probabilities together, right down the chain. So here's what that formula looks like. The probability of the whole shebang, wet grass, sprinkler on, and rain, is just a few things multiplied together.
It's the probability of the grass being wet, given the sprinkler and rain situation, times the probability of the sprinkler being on, given that it's raining, times the plain old probability of it raining in the first place. And the best part, we already have every single one of these numbers. They're sitting right there in those little CPTs we made. So all we have to do is plug in the numbers. We just grab the values right from our tables. We take the chance of the sprinkler being on while it's raining, which was super low, remember, only 0.01. Then we multiply that by the general probability of rain, and then by the probability of the grass being wet when both those things are happening. We multiply it all together and we get our final answer for that exact scenario. It's a really tiny number, something like 0.00158. And just like that, we have our answer. Okay, so we figured out the probability of wet grass. That's cool, I guess? But you're probably thinking, so what? Why does this even matter? Well, here's why. Because the exact same logic we just used, just scaled way, way up, is being used to tackle enormous, incredibly high-stakes problems, like right now. Let's just put this in perspective for a second. Our simple model had, 3 variables: rain, sprinkler, grass. Now look at the kind of variables that go into a real-world medical model. Mother's age, family income, birth weight. We're talking dozens, sometimes hundreds, of interconnected factors. But here's the crazy part. The underlying principle is exactly the same. You map the dependencies, you add the probabilities, and you ask the network questions. And this is what one of those looks like in the wild. This massive web is a Bayesian network for a real system called Mentor. It's used to assess developmental risks in newborn babies. Every single one of those ovals is a variable, like mother's age or birth weight, and every arrow is a probabilistic link, just like the one we drew from rain to sprinkler. Yeah, it looks complex as heck, but it is built on those same simple, powerful ideas we just walked through. And once you start looking, you see these things everywhere. Banks use them for credit risk, doctors use them for medical diagnoses, biologists for analyzing genes. You know that little troubleshooter that pops up in Windows when your printer isn't working? Yep, that's a Bayesian network trying to figure out the most likely problem. They're in our cars, they help with speech recognition. Seriously, the list goes on and on. So if there's one thing to take away from all this, it's this. This whole framework, it gives machines a way to reason with uncertainty, to make educated guesses. And what's really crucial is that you don't need to have all the information. You can have missing pieces of the puzzle, and the network can still calculate the most probable answer based on the evidence it does have. It allows machines to finally think in those shades of gray. Which, of course, leaves us with a pretty wild final thought. If we can really represent knowledge as a graph, as this map of causes and effects, and if we can put numbers on all those connections, then what are the limits? How much of our complicated, messy, uncertain world can we actually start to map out, to understand, and maybe even to predict?